So today let's test this adjustable switching power supply. It's a bit similar to the one I already tested, but not the same. It's a different voltage range and different current rating. And this one was donated, so big thanks for the donation. It comes in a paper box with not much on it. 3 to 24 volts, 3 amps, which also is here. Here's the model number. The input is a universal mains voltage and the output again as on the paper box. Warning, LTE power supply for indoor use only. Now of course let's try to plug it in and see what happens. No explosion. There's the potentiometer with the built-in switch, and it seems to work at the minimum, about 3.3 or 3 volts, and the maximum 24.8. In the middle about 13, 12. It seems to work with no load, but let's load it. And by the way, you should always put some filter over an LED display to make it better readable. You can read it easily like this, but without it it's very tricky to read. This is probably better. Well, this one, even in a bright light, it's readable. And readability isn't really about the brightness, it's about the contrast between the on segments and the off segments. Now you barely see anything. And when you turn it to 0, there's a charged capacitor. Still 3 volts. Now it goes down and it's weirdly flashing. That's a weird design. It has a European plug, but let's compare the size of it to a proper European plug. And there's quite a lot of difference. This one is actually quite smaller. It actually has the proper length of the pins, but the size of it is sort of shrunken. It's a dwarf plug. This is not how a proper European plug is supposed to look like. But now of course we have to load it to test it properly. I have this USB meter and my DIY test load. Then I'm not going to bother with this connector. Let's just cut it and connect a USB port to it from some dodgy charger I disassembled. Looking at the diameter of the wires, I've actually seen a much thinner in a 3 amp power supply, but it could be better. I'm checking if the red is actually positive and the black negative, which is something you shouldn't take for granted in Chinese electronics. And the voltmeter seems to be sort of accurate. 24.7 almost and 24.8, 3.15 and this one 2.89. Not the most accurate at the bottom of the range. And of course below about 4.5 volts. The meter is dimmer and it flickers visibly. I guess the meter actually isn't supposed to run at such low voltage. Let's set it to, let's say, 5 volts. I set it to 5.03. Here it shows 4.96. It's close. I should probably keep the filter on it so you can see it. Now it's not loaded. Let's try to load it up to 3 amps. Gradually going up with my test load. And the voltage goes down, but it's not shutting down yet. Going up. Does it make 3 amps? Well, it actually makes it, as the voltage drops to 4.17 volts. Interestingly, here it actually stays at 5 volts almost, but the resistance of the cable actually brings it down by about 0.8 volts. But now let's try, let's say 12 volts. This is it with no load, and let's go up. The current goes up and the voltage goes down because of the resistance of the cable. The power supply itself is regulated, but the resistance of the cable drops a lot of voltage. And it's making 3 amps. But we're again losing about 0.8 or 0.9 volts on the cable. Let's actually try 24, the full voltage. And it's actually making almost 24 volts, 23.9 at 3 amps. Not bad. Of course the question is, can it do it continuously? First let's try 12 volts at 3 amps for a couple hours. No explosion after 10 minutes, but the voltage regulation seems to be drifting down thermally. After 1 hour it further drifted down. 2 hours. And some thermal imaging. 69, 71 degrees Celsius. The voltage thermally drifted down to 10.8 volts. I unplugged it and left it to cool down overnight. And I did not touch anything. Now let's see what voltage it produces with the potentiometer in the same position but in a cold state. 13.1 volts. So going from a room temperature to its equilibrium operating temperature, it drifts down from 13.1 to 10.8. Well, that's called a stable voltage regulation, isn't it? But now let's go to the maximum, basically the full load and the full voltage. Above about 30 or 40 watts, my test load needs a fan of course, and let's leave it running. Microwave oven fan, this should be enough to keep it cool, while dissipating about 72 watts. After 1 hour it drifted down to 22.3 volts, or this at the end of the cable. After 2 hours, 21 volts at maximum, and about 20.2 volts with the drop of the cable. And of course some thermal imaging. The surface, the hot spot is about 93 degrees Celsius, bloody hot, and I can smell the typical toxic smell of a cheap Chinese plastic getting super hot. The bottom, over 100 degrees Celsius, bloody hell, that's baking. But now of course let's try to open it. Can I somehow pry it open? And that's it. It absolutely stinks of a baked circuit board inside. And the layout of it is completely different than the power supply I explored some time ago, which from the outside looked quite similar to it. But inside of it it's constructed completely differently, and the potentiometer is actually closer to the mains input, unlike in the other one where the potentiometer was closer to the output. Here's the mains inside with the fuse, the bridge rectifier made of discrete diodes, the smoothing capacitor on the primary side, 47 micro 400 volts. Here's some diode. Here's the control chip, some small auxiliary capacitor, I guess some current sensing resistor, sensing the current in the drain of the transistor, the main primary switching transistor, some startup resistor maybe, the optocoupler here, and this side of it. You can see the switch in the potentiometer, which basically switches the mains. The mains goes via the fuse and then this potentiometer switch into the bridge rectifier, from the bridge rectifier into this smoothing capacitor. Is there any inrush resistor in series? I don't see any. It's the fuse and the switch in the potentiometer. The neutral goes straight into the diodes, and no inrush limitation, no resistor or NTC thermistor. Of course these terminals of the potentiometer are on the secondary side, but basically almost touching this capacitor, as the capacitor can actually move in it as you drop it. The only isolation really is the heat shrink on the capacitor, which might not even be meant as a safe insulation. The switch is on the primary side, but the terminals of the potentiometer, the resistor trays, are on the secondary side. Also, this is the isolation distance. There is a slot, but the mains connection and the potentiometer connections going to the secondary side are super close here. The distance is slightly over a millimeter. And the toxic smell of baked electronics that comes from it is absolutely horrible. This heat sink of the switching transistor is actually not that far from touching this resistor on the primary side, but also touching this capacitor, which actually goes from the primary side to the secondary side. It should be a safety capacitor. We will take a look at it if it actually is a safety class Y1 capacitor, as it should be, between the primary and secondary side of a power supply without a grounded output. This is the isolation distance under the capacitor, slightly over 2 millimeters, less than 2.5. All these components here are on the primary side. This is probably the Snubber network on the primary. This capacitor touching the core of the transformer, freight core, which is actually conductive. But also this heat sink with this screw can touch it. And this is on the secondary side. The heatsink actually is soldered here and connected with the secondary side. Here are the secondary capacitors and an LED which nobody can see because there is no window or any transparent insert in the box. And also, as it was super hot, this sticker actually distorted on the box. And the hottest area was probably above the transformer, but also these two heat sinks contributed to it. And of course the secondary heat sink has a double diode on it, but it's used as just one diode, both sections in parallel. And as you can see on the board, the primary side and the secondary side are a bit convoluted. Some discrete SMD components, resistors and capacitors. There is one transistor and a chip, probably a TL431 reference. That's the 3-pin chip, of course. And the transistor. Here's the capacitor between the primary and secondary side. I don't really see the marking on it. I will have to disassemble it to see it better, but before this, I want to run it again for a couple hours and then quickly remove the cover and see the inside of it on a thermal camera. Of course, once I open it, it cools down, so I have to be quick to actually see the real temperature the components have inside of the closed box. I also don't like these thin wires, low voltage wires not meant for mains voltage probably, going to this module. These are on the secondary side but go around the mains side. And now I noticed something even more concerning. The pins of this display of the voltmeter actually poke into this capacitor, and this is on the secondary side. This capacitor is on the primary side, and these pins are actually poking into the capacitor, potentially poking even through the heat shrink, and basically bridging the primary side from this capacitor into the secondary side through the voltmeter module. Jesus, that's bad. So far this seems to be the most likely way of the mains voltage getting to the output. This pin is poking into this capacitor, and of course its aluminum body isn't isolated from the internals safely. Is it actually poking through the heat shrink? Not yet, but it could actually come any moment, especially given that it was running super hot, and this would soften the heat shrink and this foam pad. And also the user pushing against it or squeezing it or putting anything heavy on it could be easily the last straw for these pins to go through the heat shrink here. So let's bake it once more, and note that the voltage is higher when it's cold. Something's 164 degrees Celsius here. It's a resistor, this transistor, 122, the diode, 135, 160 degrees Celsius, the winding in the transformer. It actually activated the protection in the thermal camera. That's crazy. Is it the diode? 170 something, it's already cooling down a bit. 180, 190 degrees Celsius. These electrolytic capacitors have to be absolutely baked. 134 degrees Celsius. Again activating the protection in the camera. This area actually is quite cool. The voltmeter not very hot, but this is an absolute hellscape. It's like in a furnace. On the bottom of the board, and with the macro lens, that's the diode here. And the other side an SMD resistor over 150 degrees Celsius. And of course here's the schematic of it. It's basically a flyback switching power supply with an old school control chip 3843, which is like 3842, just the enter voltage lockout thresholds are lower for the supply voltage. The mains comes in here via a fuse and the switch in the potentiometer. There is no inrush current limitation, no interference suppression. It's just rectified and goes into this primary smoothing electrolytic capacitor. Here's the primary with the Snubber network and the super hot diode, the startup resistor, and then the chip is powered using this auxiliary winding. This winding is rectified and smoothed by this small electrolytic capacitor, and it powers the chip via the pin 7. The pin 5 is the common 0-volt rail of the primary side, and the pin 6 is the output for the gate of the switching MOSFET, switching the primary. Here is the current sensing resistor. It senses the current using the pin 3 of this chip. The chip has a built-in regulator of 5 volts, pin 8, and this is used for the oscillator, which is connected to the pin 4, and pins 1 and 2 are used for the voltage feedback. The chip reduces the duty cycle when the pin 2 exceeds 2.5 volts, or when pin 1 is pulled down. In this case they're using pin 1 to control the duty cycle for the voltage feedback, and the optocoupler phototransistor is connected to it. And here is its LED. The secondary is rectified using this diode. It has a Snubber network, the indication LED, some loading resistors, smoothing capacitors, which are being completely baked here, and the voltmeter module. Here's the output, and the voltage sensing on the secondary side. I decided to draw the schematic because I was curious about two things. The first one was how the control chip gets about a constant supply voltage for it, when the output voltage can be changed in 8:1 ratio. If the auxiliary winding is rectified in a flyback direction, the voltage for the chip would be basically changed in the same ratio as the output, which would be a way too wide range for it. So I guess the auxiliary is rectified in forward here, because then the output voltage on it doesn't really depend on the output voltage, it depends on the input voltage on the smoothing capacitor, which doesn't change that much, even though if it's actually really for a universal mains voltage, then it's still going to vary in about 2.5:1 ratio at least. That's still better than 8:1. I should make a measurement of the voltage on this capacitor, and I should also make an autopsy of the transformer to see how the winding is oriented. Well, I have to open the transformer anyway to see how safely the windings are isolated, And the other thing I was wondering about was how the hell the output voltage can drift by almost 20% when I could see a TL431 voltage reference in the voltage sensing, which is typically about 1% accurate. And this is the explanation. The LED in the optocoupler can be driven by this reference, but also by this transistor. And the voltage reference has a non-adjustable voltage divider made of these resistors, and it's basically setting the maximum voltage. But the actual voltage adjustment with the potentiometer is using just a transistor. And this makes absolutely no bloody sense. And they have the accurate voltage reference here, but the actual adjustment depends on the voltage drop of the base 2 emitter of this transistor, which of course has a massive thermal drift. The hotter the transistor, the lower the voltage drop base 2 emitter, which also shifts the whole voltage setting down. They put a Schottky here, maybe trying to compensate for it, which surely works well. It might make a little bit of sense. This divider is basically setting the maximum, so even if the potentiometer goes open circuit, it doesn't go over about 24 point something volts. But in a normal operation, the voltage is actually sensed using this transistor with a massive thermal drift, which is an absolute disaster in combination with the circuit board getting bloody hot. The adjustment should have been in the divider of the TL431 reference, which is accurate. If they wanted some protection against the potentiometer open circuit, or basically an open loop protection, they might have used some Zener, or maybe a combination of a Zener and a thyristor as a crowbar protection, but definitely not this. And also based on the temperature of this diode, I guess it's not ultra fast. It should be an ultra fast diode, but it's probably a too slow one, so it has very high reverse recovery losses. Because when the voltage changes from forward to reverse, every diode needs some time to turn off. It never happens immediately. And in a lot of cases the diode in this Snubber network has a series resistor, something like 100 ohms, couple hundred ohms, which doesn't increase much the voltage drop in forward but softens the reverse recovery, or limits the current in reverse before the diode turns off. I should measure the secondary waveform, maybe the waveform on this winding, and also the voltage on this capacitor. Let's see the secondary waveform at a full load. And more duty cycle with more voltage setting. And you can see the flyback voltage changing with the setting, not the forward one. This depends on the rectified mains voltage. And here's the auxiliary winding, which, as I expected, is rectified in the forward direction. And measuring the supply voltage of the chip, this is at full load minimum voltage, 22 volts. It goes up a bit but not much with the voltage setting. Full load maximum voltage 23.4 volts. We're about no load, actually lower with less load because of the very low duty cycle. Minimum load, minimum voltage, just 8 volts. And the LED is flickering here. It's actually not working properly in this setting. With very little or no load and a low voltage setting, it can't stably operate. This display flickers, the LED flickers. You don't see it in camera, but the under voltage lockout actually cycles now. And it says it works down to 100 volts. I'm really not sure about that, but let's try Variac. Let's see, this is from a Variac. No load minimum voltage setting. You can see this flashing, the LED flashing. It just does not work properly at 100 volts. Increasing the voltage. The LED is still flashing. It actually starts working well, about with the potentiometer in the middle. Let's try to load it at 3 amps. And it's cycling. Does not work at 100 volts, or very intermittently. There's not enough voltage for the chip. At maximum it's just 18 volts. 1.5 amps, 50% load. It actually operates at this load. But it doesn't at full load, and it also doesn't at no load. At 100 volts, it only works when loaded from 250 milliamps to 2.2 amps. Not with no load or very light load, not with a full load. In some conditions, the under voltage lockout of the chip kicks in. And 240 volts. The supply voltage of the chip is kind of excessive. And this impulse also goes into the gate of the MOSFET. Some MOSFETs are rated for 20 volts, some for 25, some for 30 volts. The MOSFET gates, I mean, of course. It could actually exceed the rating of some MOSFETs. The chip supply voltage doesn't depend much on the voltage setting, but it depends greatly on the mains voltage. As I reduce the mains voltage, the chip voltage basically goes down proportionally. There's a lot of modern flyback switching power supply control chips which have such a low current consumption that you could completely get rid of this auxiliary winding and just power it via a resistive dropper from the rectified mains and add a zener parallel to this capacitor. But this old school chip draws quite a lot of current. So powering it from a rectified mains using a resistive dropper isn't really viable because the resistor would have to dissipate multiple watts. I mean, it's possible but not very practical. Or if you insist on this chip, you could put some voltage regulator here maybe. And the resistive trace in the potentiometers on one side of the isolation line, the contacts on the other one. But I'm not sure if these two sections are isolated from each other safely. Is this potentiometer even meant to have safely one side on the primary side and the other one on the secondary side? I guess it's the same design as the other one. The one in the other power supply, just a different value of the resistive trace. And here's the switch, very close to the metal housing, and the metal housing very close to the resistive trace. I don't really think it ensures a safe isolation distance like this. Especially if these contacts fall apart. This can actually easily come off and potentially touch something else. And bridge the mains contacts to the secondary side. Here's the double diode, here's the switching transistor, and here's the capacitor between the primary and secondary side, 2.2 nano, which to my surprise is a class Y2 capacitor, but it should be a class Y1 here. The board says class Y1 too. Here is the missing values to the schematic. Some markings were not visible and the SMD capacitors had no markings. So I had to remove some components to see the markings and desoldered the capacitors to measure their values. And the crazy hot diode is FR107 and its reverse recovery is 500 nanoseconds, which is actually bloody slow in comparison to a very common UF4007, which is 75 nanoseconds. But of course Snubber networks are quite a black magic. And more often the components in an R-series Snubber network are in this order, but it doesn't make much difference. But what makes a difference is how fast this diode is, the value of this resistor and maybe the value of this capacitor. And of course traditionally this diode was ultra fast, but then there was also a fashion wave of using a slow diode for this application, which actually had some advantages, slightly improving the efficiency and reducing the interference, because the slow diode would actually conduct in both directions for the very high frequency parasitic oscillation. The oscillation of the leakage inductance with the winding straight capacitance and the drain to source capacitance of this transistor, which caused a lot of interference because it was typically multiple megahertz. But the slow diode at this frequency basically conducts both directions and adds this capacitor into the resonance, significantly reducing the interference and also reusing some of the energy from the capacitor and getting it to the secondary instead of dissipating all the charge in this capacitor in this resistor. But for the circuit to benefit from a slow diode, you have to choose the right resistance for this resistor, typically higher, maybe a lower capacitance for this capacitor, and also add a series resistor to this diode, which also dampens the oscillations, reduces the Q factor of this leakage inductance with this capacitor. It might also reduce the reverse recovery losses in the diode, but I have to stress that for the circuit to benefit from a slow diode here, it all has to be designed right. You can't just blindly put a slow diode into every Snubber network. And a slow diode in this position, I believe, is only suitable for a discontinuous conduction mode. Because in a continuous conduction mode, this diode still has a current in forward, potentially, when this transistor turns back on. And based on the waveforms, this power supply is a continuous conduction mode, so it's not suitable for a slow diode here. The trick with the slow diode works in some conditions, but not in all conditions definitely. It also might not be suitable for higher powers. 72 watts might already be too high for this. Some only recommend a slow diode here up to 20 watts or so. But I guess the main reason this is extremely hot is because it's a slow diode in combination with a continuous conduction mode, but also because the proper designs with a slow diode also have a resistor in a series with the diode. But the video is getting bloody long. Now let's open the transformer. The transformer's out and let's disassemble it. There is some sticky tape around the core, the ferrite core, with an air gap because it's a flyback switching power supply. Here's the transformer without the tape. It smells baked, but let's bake it even more using my melted hair dryer to unstick the core. I really don't think I made it hotter now than it was in operation. Here's the air gap in the middle, and now let's see the windings. This insulation on top. And some winding. This is the auxiliary. And this one seems to be kept clear of the other windings. And it seems to have 4 turns. 4. And then some insulation under it with no gaps but a bit baked. 1 layer. 2 layers. It's not easy to remove the insulation, it's sort of melted and fused together. Then we have the primary, which seems to be a split primary. The middle is actually on this pin, which is not in the board. 1/2 of the primary is probably above the secondary and 1 below. 1 turn, 2, 7, 8, 8 turns. The ends of the secondary are not covered, but at least the primary wasn't going all the way to them. Here's another insulation. And the secondary here, quite a random mess. So that's the secondary, made of 4 parallel wires to reduce the skin effect, and now probably the worst part. This secondary is actually sitting right on the ends of the primary here. The bottommost turn of the secondary, touching these wires here, which are the primary here and here. There's really just the lacquer isolating it. Let's make an even closer detail. The secondary sitting on this end of the primary here. And the other end of the primary, and again the last turn of the secondary sitting on it. And the secondary is 1 turn, 2, 9, 10, 11 turns. And probably 3 more wires parallel to it. 10, 11 again. All 4 windings have to be 11 turns. Then you again see the exposed ends of the primary, its lower section, and the insulation. And the primary. Some part of it seems to be darkened. 26, 27, 28, 40. Measuring the diameters of the wires. And to my surprise, it's not a copper-coated aluminium, but it still might be some alloy, not a pure copper. And that's it, completely reverse engineered, including the numbers of turns and diameters of the wires. So let's sum it up. A small powerful switching power supply with an adjustable output voltage. That seems like a great idea, but I really wouldn't recommend it after seeing all the problems in it. No interference filter, a poor isolation distance on the board, the voltimeter module poking into this primary capacitor. A class Y2 capacitor between the primary and secondary side is better than an ordinary capacitor, but it still should be a class Y1 for this application. I'm really not sure about the isolation inside of the potentiometer, which is safety critical here. No inrush current limitation, a thin output cable, an extremely high operating temperature. The switching is not stable in some combinations of the input voltage, output voltage and the loading current. It can't operate down to 100 volts minus voltage as it claims. This all makes it quite questionable, and after seeing the secondary sitting on the ends of the primary inside of the transformer, it's an absolute hell no. A self-baking, thermally drifting, interference-generating electrocution house burner. I guess the Snubber network with the overheating diode was put together without knowing what they're doing, in a similar fashion to this voltage sensing circuitry, which doesn't make much more sense than this glaring super bright blue LED inside of a black box. And I'm glad I didn't have to use my fire extinguisher here. So that's it, the video got bloody long, but if you like my videos, please consider subscribing, supporting my channel on Patreon or using the thanks button, based on the value you received from my videos. And a big thanks to all of you who already support me. Without you, this channel wouldn't be possible.